Okay, we're going to use graphical analysis again to solve our third problem here. So we're driving along at 25 miles an hour, but we need to slow down to before we get to the new speed limit sign. But we need all that needs to happen within 40 meters. It'd be easy if it was 10 seconds, but here it's 40 meters, so we're going to have to get some good relationships out of the graph. So I'm not even going to put numbers on the graph here other than 0 and 0. We're just going to use the graph to come up with some equations. So we start at some VI that's relatively quick, and then we need to slow down to a VF that is slower, and we're going to do that in some amount of time, though we don't know how much. Some amount of time, delta t. Okay, so the constraint here is that we need delta x can't be any more than 40 meters. So if we solve for the acceleration needed to get us to make this happen in 40 meters, then we'll have the minimum acceleration needed. So we need to figure out how to get our delta x from this graph, and that is the area of the graph. But this graph is a trapezoid, so how do we get the area of a trapezoid? Well, we need the sort of length of the trapezoid here, and then the size of these two bases, and we put them together. So this base is VF high, and this base is VI high. So what we want is 1/2 times the sum of those. Physically, what that gives us is the average velocity, by the way. And then it's this long, it's delta t long. Okay, so we know what the VI and the VF need to be, so we could figure, there are a few ways we could solve this problem here. We could solve for the delta t here, and then just do VF minus VI over that. That's probably algebraically the easiest way to do it. We could also introduce A into the calculation by re-expressing VF. But let's do it the easier way here. So delta x we know is 1/2 times VI plus VF. We know both of those numbers, times delta t. So what we want to do to solve for that is multiply both sides by 2 to get that 2 over there, and then divide by VI plus VF. And we know that acceleration is delta v over delta t. That's just the definition. So delta v is VF minus VI over this last expression that we got. So 2 delta x over VI plus VF. And we simplify this compound fraction by moving this up to the numerator. You never want to leave a compound fraction like that. It's very difficult to read. And I'll finally clean up the numerator by multiplying this through, because this is a difference of the difference times the sum, so we have a difference of squares on the top. It's a nice compact answer. So what we have is 25 meters per second squared. Oops, that's the initial. 15 meters per second squared minus 25 meters per second squared over 2 times 40 meters. And what we get is -5 meters per second squared. So up in the numerator we had meters squared over seconds squared. We divided out one of those meters, which left us with meters per second squared. The negative makes sense here because the velocities we said were positive. It's slowing down, which means the acceleration is the other direction from the velocities. The negative acceleration by itself doesn't mean that it's slowing down, but in combination with the positive velocities, it does.